In this video, I want to take some time and review topics relating to bivariate data, mainly talking about regression and correlation and those kinds of things. And a lot of this we've covered pretty recently because of the recently talking about hypothesis testing. So the first thing, DOFs. Let's just remind ourselves what the DOFs stuff stands for. And I've taken my data that you see, the hours studied and score and exam here to the right, and I'm going to make a quick scatter plot of that because that's really what we're looking at. And let me show you what that looks like, and then we'll do DOFs with that. Okay, so here it is, and what the D stands for is direction. So you see a positive trend here. Okay, so our direction would be positive. Outliers. Outliers means that really if you put a line through this data, or whatever equation you think would fit best, are there points that are far away from that trend? I would say no. I don't think that there are any points that are far away from the trend. They pretty much fit what that line predicts. Form means what type of equation would work the best. I think with this, linear would look pretty good. The points seem to fit that line. And strength is really kind of a generalization of correlation. You know, how strong is it? Do the points really fit, or is it just okay around the equation? I think this is fairly strong. Okay? So again, memorize those four things: direction, outlier, form, and strength. All right, correlation. Here are some things I want you to remember about correlation. Okay, there are no units on correlation. Correlation does not have a unit associated with it. There's no explanatory and response relationship, and therefore there's no causation. The other thing I want to call attention is there are always questions that come up of what would happen if I switched my X and my Y, just flipped them. And the answer is nothing. That wouldn't affect the correlation at all. It wouldn't make it negative. It wouldn't change it at all. And it measures linear relationships. Okay, linear relationships. Next, R squared, or the coefficient of determination. Okay, this is the book definition of R squared. I think I'd like to change it just a little bit. I would say it's the percent variation in Y that is explained. So you could maybe, like I said, maybe I could even shorten this. The percent variation in Y that is explained. Oh, I want that. That is explained by variation in X. And of course, you put the context in there. So that's a shorter way to write it. It's the percent variation in Y that can be explained by variation in X. So for our first example here about hours studying and score, whatever the R squared was, we'd say that's the percent of variation in score and exam that can be explained by the number of hours studied. Okay, let's now interpret the slope. All right, the slope is the amount by which the Y variable is predicted to change when the X variable increases by 1 unit. So what you would say for something like this, this example is, it's the amount the score is predicted to increase for every additional hour of study. Okay? So again, what is predicted to happen to score when our study increases by 1 unit? Okay? Now, the y-intercept. The y-intercept is the predicted amount of the response variable when the X variable is equal to 0. So it's the predicted score when hours studied was 0. The key word here is predicted. All right, we really want to make sure that word is part of this in every definition you use. These three definitions: coefficient, slope, and intercept. If I could move this so you can see all of them. These three should be things you have committed to memory. They're going to be on the multiple choice for sure, where all you need to know is what the definition is, and you're going to be able to answer the question very easily. All right, so let's keep going. The least squares regression equation. For the most part, this just means regression line, and for the most part, this is something that you'll be able to do on your calculator. You'll go to Stat, calc and do linear regression, and you'll get output that looks like this. So again, there's our our y-intercept, the amount predicted when you've studied no hours. Slope, the amount your score is predicted to go up for each additional hour of studying, r squared. So 75% of variation in score can be explained by hours studied, and by variation hours studied, and your correlation. Okay. There are times that you may have to think about doing this on the exam where you may use your formula sheet. Really, the only formula you need to remember is that slope is equal to correlation multiplied by change in y over change in x, where those are the deviations. And that formula is provided to you on the AP exam. Okay? Now, residuals. Residuals are the actual data point minus what was predicted from your line. Okay? So AP, right? AP stats, actual minus predicted. Residual plots. I'm going to just quickly kind of draw what a residual plot looks like. A residual plot, remember, has the original explanatory variable, and then here it has the residuals. I better write residuals so you don't think it's response variable. So, for example, if hours studied is my original explanatory, 2 here, I'd put 2, and then I would calculate what the residual was for 71. That's the actual, figure out what the residual is, and then I would plot the residuals. What we look for in a residual plot are trends, because trends mean that something else would fit better, a different type of equation. Okay? Now, outliers and influential points. Let's just maybe draw a couple of quick, if I've got some points that look like this, and I draw a line through them, like that. An outlier would be a point like this, that is far away from the trend. Whereas an influential point, let's say I had this. These are my 4 points. And then I added this point up here. So now my line looks like that. This would be an influential point because it basically took us from a correlation of 0 to a very high correlation. So outliers are points that are far away from the trend. Influential points are points, they can be outliers, but they can also be the points that set the trend. They dictate what kind of our eye sees as we make the best looking equation. Okay? So remember, outliers, this isn't an outlier. Even though it's far away from the original data, it's not an outlier. It's an influential point. Okay, in terms of computer output, some things to just remind yourself of. This comes from Minitab. We've got the coefficient, next to constant. This is your y-intercept. This would be your slope. You can even see it up here. It should have a cost hat, but that's how we write it, right? Parentheses. Standard errors. So we don't usually use any of the information in the y-intercept row, but this is the standard error for the slope. This is the t-statistic if we ran a test on a null of 0, an alternative. And this is the alternative not equal to 0. You can see r squared right here. One thing to maybe think about, and kind of put 2 pieces of information together. R squared, if you wanted the correlation, you'd take the square root. And when you're solving for a square root, you typically think, well, it could be plus or minus. Since income is positive, I know that my r was positive. Okay? If the slope had been negative, you know your correlation is negative. Because remember, correlation helps us get the sign, that positive or negative association. So you may sometimes have to put some pieces of information together. We don't ever use r squared adjusted. Okay, you can just kind of cross that out. We will not be using that. This value right here, this S, this is kind of a standard error for your residuals. Basically, a similar definition to standard deviation, it's a typical distance between the individual data points and the line. Much like standard deviation is a typical distance from the individuals to the mean. But this is the typical residual. Okay, the hypothesis test. You'll recall, we just got done doing those. The state, plan, do, conclude. The state was that that beta was 0, and our alternative, of course, would be that beta, and then we can kind of fill that in, and then define. Beta is the population slope between the two variables. Hours studied and score on the exam. The plan was always kind of given to us, right? It always said that all conditions were met, but let me just remind you what those conditions were, even though I don't believe you'll ever need to be responsible for them. Was the data linear? Is the data independent? Are the residuals normal? Are the standard deviations approximately equal? And was it collected randomly, a random sample? Okay. The do, T statistic. Remember that the degrees of freedom is n minus 2, and a p-value. And of course, your 3-part conclusion, right? I'm just going to write 3 parts. We've done an awful lot of these, but let me just say aloud what they are. What are you doing with the null? Reject or fail to reject? Why did you do that in terms of the p-value? And then what does that mean? If you reject the null, you're saying you have evidence of the linear relationship. And, depending on what this was, it might be I have, evidence of a positive linear relationship or negative. And then, so those are your 3 parts, okay? Now, confidence intervals, sometimes people have this built into their calculator, but most of the time the confidence interval actually comes on a computer output problem. And what you need to remember is the confidence intervals are always this formula from the formula sheet. Okay, it's always the statistic we're trying to estimate plus or minus the critical value times standard deviation of statistic. So for this particular computer output problem, it would be, our statistic is 0.51145 plus or minus. I'm just going to leave this blank. We would use our chart to get T star. And then the standard deviation of the statistic is 0.02325. So remember, to use the chart, we simply go to the bottom, find the percent we want, scroll up to the degrees of freedom, and that gives us our critical value. Okay, so this has been an overall kind of review of all of the things we've done with bivariate data.